All right, so this will be the last lecture on shear flow and shear stress distribution. So far we have talked about shear flow, which is a force per longitudinal length. So if I take a horizontal cut through a beam, looking at it in elevation view, the force per length longitudinally is what we've defined as shear flow, and that's required basically to balance any change in moment. So if the moment has a gradient to it, then we need to have some shear flow to make sure that we're in equilibrium. And it turns out, as we derived, I think, a couple lectures ago, that the derivative of the moment, dm dx, actually equals the shear force, which is V. So we also saw that with the moment diagrams, moment and shear diagrams that we had done previously. And so what I want to do today, anyways, that was shear flow. And then shear stress is if I take that shear flow and I divide it by the width of the beam in cross section. So instead of it being a force per length, it then becomes a force per area, which is shear stress. Right? So what I want to do today is talk a little bit about conceptually, how to think about shear flow and shear stress and how these things relate to one another. Okay, so I have a cross section drawn here, and I will let me see here, 1, 2, 1, 2. So I guess it's right in the middle. So this guy here is my neutral axis. Okay, so we could look at two separate cuts, right? So the first one I'm going to take, I'll do it in, I guess I'll do it in black here. So I will take this cut at this location here, right? And it is going to have this as my y. I'm going to call that y1, okay? And then the q associated with this guy is going to be this area here. So I'm going to shade this or highlight this in blue. Right, so that would be that area, right, times a d, right? And that d, just so we're sort of being clear here, is actually this d here. So this becomes d, right? So that is to the centroid of that area, right? So I can write over here that q1, right, which is a function of y1, is simply area 1 times d. Right? And this guy here is the area 1, right? So that's my capital Q, first moment of the area, as a function of y1. So that is not times y1, it's just as a function of y1, okay? Good. And then we also have a width that I need to consider here, which would be sort of this out-to-out width here. And this guy I'm going to call B sub f, right? So that is the width of the flange, right? Okay, so if I'm going to write the equations for shear flow and shear stress here, what I'm going to do is I'll write Q, and that is a function of y1, right? So it's actually at y1, that level, not where the d is taken to, right? But y1, that is a function, or Q is a function, shear flow is a function of y1, and that guy equals the total shear force, right, which is, comes from the shear diagram, times Q1, right, divided by I, okay? And so this guy, Q1, is a function of Y1, right? And it's actually this guy right here. So you could see as I take Y1, let's say a ½ inch higher than where it is now, you could see Q is going to drop, right? Why? Because the area gets smaller and the D increases, but the D doesn't increase by much, right? So Q gets bigger the closer we get to the neutral axis, right? Okay. So then we can also look at tau xy as a function of y1. And the only thing I've got to do there is I take this same, shear flow, and now I just divide it by the width of the element that I've sort of cut through. So in that case, this becomes the width of the flange. Okay? So that's it. If I ask you on an exam, halfway through the top flange, what is the shear stress, right? Or what is the shear flow, and then what is the shear stress? You're going to calculate the Q for the area above where I'm telling you to take the cut. You're then going to, that's capital Q, then I'm going to calculate the shear flow there. And then finally I'm going to divide that shear flow by the width of the flange, because that's where I cut through. And that's going to give me shear stress, right? So that's shear flow and that's shear stress. So now let's take another cut, and I guess I will do this in, what do I want to do this in? I guess I'll do it in red. So now I'm going to take a cut here, right? So now my Y bar, or sorry, my Y, I'll call it Y2, right, is within the web, okay? And then I'm going to hatch this. Hopefully this comes out okay. But it's this area here, right, that I am taking the Q for, right, the capital Q, the moment of the first moment of the area. And then I'm going to dimension, and you can see I'm gonna put a, so that is a sort of the universal symbol for centroid, and if I dimension to that location, right, that is going to be my D, right? So I'm taking the area there, you can see it's shaped like a T. I'm finding the centroid of that area, right? And then the distance between the centroid of that area and the neutral axis is D, right? So in fact, maybe what I'll do, let me go back a second. I'm going to call this guy D1, so there's no confusion. And then I'm going to call this guy D2, right? So I'm just sort of conceptually calculating the shear flow and the shear stress in these for these two locations, Y1 and Y2. Okay, so Q2 here is a function of Y2, right? And that is just equal to this second area here, A2, right? And that's got to be times D2, right? So that's its moment arm. And then similarly, my shear flow, this is the shear force per longitudinal length of the beam, right, is going to be V times Q2 over I. Notice that I is always the same. I does not change at all, right? So I is the moment of inertia of the entire cross section, right? It is not the moment of inertia of the area above the cut, right? Where I take the cut only affects capital Q. That's it, okay? So that's my shear flow, lowercase q. And then my tau xy, also a function of y2, is now VQ2 over I, and now I'm going to divide it by not the width of the flange, but the width of the web, right? And so I guess what I'll do is I'll show it here. Right, so the width of the web, the closest to the neutral axis, basically where I'm taking that cut, that's what I divide shear flow by to get shear stress. Again, that's the second sort of dimension that I need to divide it by. Shear flow is a force per length. I divide it by another length. In this case, it's the width of the beam, and that gives me a force per area. Right? And that is actually shear flow, right? So this guy Q here, let me just, for completeness, show that it's actually that Q right there. Right? So now let's take a look at how we think these things are going to vary, right? The first thing I want you to notice is, is that there is a discontinuity at this location. Right? So what does that mean? Well, it means that if I'm calculating the shear stress above that point, so now I'm in the flange, I'm dividing it by B sub F, right? If I'm calculating the shear stress below that level, now I'm calculating it by B sub W. Right? Notice that that disconnect does not occur in the shear flow equation, right? Q is actually continuous, right? D is going to change slightly as I start getting into the web, right? And the area is going to change slightly, right? But it's more or less a continuous function, and you can calculate it and plot it. And in fact, I'll show it in the next slide. But the discontinuity comes in with tau xy, and the reason it comes in is because all of a sudden I'm taking the shear flow, and instead of multiplying it by this large B sub f, I'm now, dividing it by this large B sub f, which is going to reduce it, right, significantly. I'm now dividing it by a relatively small B sub w, right? So I would expect a significant jump in my shear stress as I go from the flange to the web, right? The way you can think about that is there's less material to take the shear flow, right? Instead of dividing it by this huge width, right, now I'm dividing it by a small width, and I'm actually going to get a big jump, right? And again, that discontinuity is not visible or present when I'm calculating the first moment of the area. So the Q1 and Q2, there's no jump there, right? Only in the tau xy, and the reason is because the width is changing significantly. So it turns out at the location of where the flange transitions to the web, I actually have two shear stresses, right? If I take it an infinitesimal level above where that transition occurs, right, I have much less shear stress than if I take it an infinitesimal distance below, right? And again, the reason is just that the width is the width is changing, right? So I basically have two widths. If I'm a little bit above, I use the bigger width, gives me a very small shear stress. If I'm a little bit below, I use the smaller width. It gives me a much larger shear stress, right? Now, in reality, there is actually a relatively smooth transition there, but we won't get into that. You need to look at some of the sort of three-dimensional effects. But for the time being, and I think this is generally what is used. In fact, I know it's what is used in design. So for all intents and purposes, at least in this course, this is this is the sort of the ground truth here. Okay, so let me now move on to plotting this. So I'm going to redraw that, and I'm going to shrink down the flange width just a little bit. Again, this is all sort of conceptual, and the reason I'm doing that is just to provide some room to plot the shear flow and then the shear stress. So let me plot the shear flow. I guess we'll do that in black. So this guy is going to be Q as a function of Y. And then in red, I will plot the shear stress. And so this guy is going to be tau xy as a function of y. And then I just want to make sure that we know exactly where each sort of feature in the cross section comes across those lines. Right. And then, of course, we've got this neutral axis here. So this guy is my neutral axis, okay? All right, so let's start, right? So if we look at Q sub y, right, the only thing that varies there, right, as we go down the cross section is capital Q sub y, right? So that's the only thing that varies. So all I've got to do is look at how the area and then the moment arm between that area and the neutral axis will change, okay? And what you find out is when you're in this region here, right? Right? What it means is if I go down a small amount, right? Oh. If I move down a small amount, right, you can see I'm actually increasing my area pretty significantly, right? So my area is going way up, right? And why is that? Because the width is so large. So any drop in, as this line that I've drawn there starts to drop, the area above it is pretty is growing pretty rapidly, right? Again, everything is relative, but for example, if it's a ½ inch down from the top of the top flange and I move it another ½ inch down, I have doubled the area, right? So in that location, Q is actually increasing relatively rapidly, right? And what that looks like, if I'm going to plot that here, is it looks something like this, right? So Q, and because this is symmetric, this is sort of the underside of that, right? So you could see it's a relatively rapid increase in Q, again, capital Q, the first moment of the area. It's a relatively rapid increase in Q as I begin to move down, right? So let me just do this again. Okay, and now when I'm in the web, right, and now when I take a cut here, right, if you look, this portion, right, let's just say visually, that portion is 5 times, right, the area of this portion, right? So now what has happened? Now I have moved down, again, double the width. So if the top flange is 2 inches thick, I've moved 2 inches now into the web. So I'm 4 inches down from the top of the cross section, right? But I've only increased my area by 20%. Right? So now you could see Q is actually increasing much less rapidly in this region, right? And if you plot this out, and you can do so, in Excel, because you know how to calculate the area, times the moment arm, D, right? And what you'll find is that it looks something like this. Okay. So I am going to highlight this guy in blue, just so we can sort of clearly see how this is going to, okay, like that. So that's my shear flow, okay? You can see it is continuous, right? There is no big jump anywhere, okay? So now all I'm doing is, for the shear stress, what I'm doing is I'm going to take a cut here, right? And you can see there, this guy is my B sub F, right? So any shear flow that is in that area is going to get divided by this B sub F to turn it into tau xy, okay? And you can see it's going to get divided by a very large B sub F. And so here, right, it's going to look something like this, right? All of a sudden, it has shrunk significantly, right? And the same thing is going to apply down here, right? Because it's a symmetric cross-section, right? Now, as soon as I jump into this area, right, and now I make this cut, so this is sort of cut 1, right, and this is cut 2, right? Now, all of a sudden, instead of dividing it by B sub F, I'm dividing it by B sub W, right? So this guy is going to jump, right? So I have all this shear flow, and at this location here, right, it was first being divided by B sub F, which was dropping it significantly. And as soon as I moved below that, all of a sudden it gets divided by B sub W, and now it jumps, right? The B sub W is in the denominator, so the smaller it gets, the larger the shear stress gets, right? And so what I end up with is something that looks like this. Okay. And then we're back to this same, sort of distribution, right? So one way to look at this, it's a very good way to look at this, right, is that, maybe I'll do this in, I'll do it in green. It sort of looks ugly, but I think the point is just so you can see the difference. So this part here is divided by B sub W, right? And that's what gives us that part of the diagram, right? And this part here is divided by B sub F, right? And that gives us this part of the diagram. And of course, this one down here is also divided by B sub F, right? So it gives me that part of the diagram. And that's why there's a discontinuity, right? So this location right here, right, that point is just this shear flow divided by B sub F. This point here, right, the jump, is that same shear flow now divided by B sub W. Right? Since B sub W is much less than B sub F, I get this big amplification. Okay. So then let me just highlight this here. I guess I'll do it in pink. Probably should have increased the size of the marker. Okay, so it looks like that, right? So these are the diagrams that conceptually I want you to sort of understand, you know, how to draw, how to explain them, right? So let me try to conceptually explain what is happening here, right? So in the flange location, right? So this location here, right? You can see because as I start moving down towards the neutral axis, my area is increasing significantly. So my Q is increasing significantly. So the way you want to think about that is that there's a lot of material there that is taking, you know, that is subjected to some shear stress, right? So I'm collecting a lot of shear flow, right? If that makes sense. So in a thick part, so where the width is relatively large compared to other portions of the cross section, you would expect the shear flow to actually be fairly steep, right? Because as I move down, all of a sudden I'm collecting more and more shear flow, right? Because I'm, you know, that Q is changing significantly in that region, right? And then when I do the same thing, but now I'm in this area here, right? Now you can see as I move down, my Q is not changing much, right? And the reason the Q is not changing much is because you know, I move an inch further down, I'm only picking up an inch of height of the web, and the web is so thin that it doesn't contribute much to shear flow, and that's what you see, you know, here in this region here, right? Here, all of a sudden, the slope has cut off, you know, significantly, and now it's become much flatter. The reason is because it's such a thin portion of the cross section, and again, everything is relative, right? So, you know, it doesn't matter if that's 10 inches or 100 inches. It just matters, is it a relatively wide part of the cross section, in this case a flange versus a web, or is it a relatively narrow part, right? A web versus a flange. The absolute dimension doesn't really come into it here when we're just talking conceptually about this shape, right? Okay, so in terms of where the shear is actually carried, right? You could see, you could look at this and say, well, it's sort of blended between the flange and the web, right? There's a smooth transition there. But again, that's shear flow. And materials, although they feel shear flow to a certain extent, as we discussed before, you've got to divide the force by an area to actually understand what the material is feeling. And so this plot over on the right, which is vertical shear stress distribution, is much more relevant when we're talking about evaluating the capacity of a beam, let's say, to carry a certain shear force, right? And so here you could see this whole section, right? This whole section here. Ooh. This section here is actually where the vast majority of the shear force is taken. Right? So all of a sudden, I take this large shear stress and I'm integrating it over the area, right? And that's where the vast majority of the shear force is being taken by the web, right? And so when we look at cross sections here, right? the flanges here, and I think I sort of did this last time as well. So the flanges are going to be responsible for taking flexure, right? Because that's where the flexure stress is the maximum. And the web here is going to be responsible for taking shear, right? Because that's where the shear stress is the most, right? And that's why when you when you ultimately design an I section, a lot of times they're going to approximate this point here, right? So this is tau xy max. I'll just write it here underneath, right? And tau xy max is approximately equal to the total shear force divided by the area of the web. And you can sort of see that. It's almost as if it's a constant shear stress, right? I'm drawing this sort of more or less to scale, right? You see the big bump because of the change in width. But if I just take the shear force on the member and divide it by the area of the web, neglecting the flanges, that actually does a pretty decent job of approximating what that tau xy max is, right? So this is, I just want to point out a few things. I'm looking at my notes now. So this guy here is a jump due to change in width from flange to web, right? And I will also say that this here is a kink, right? It's a change in slope, let's say, due to change in width. Right? So capital Q, the first moment of the area, is still increasing, right? As we go into the web, right? It's just increasing at a slower rate, if that makes sense, right? And just so we're all on the same page, this is VQ over I, right? And this plot here, tau xy equals VQ over IB, like that. All right, so that's it for this lecture, and this should pretty much be the last thing that we're gonna do related to shear stress, shear flow, distribution in beams. You have a homework assignment that's now posted, so if you can try those problems, and then certainly bring questions to office hours or